Wouldn't it be great if a robot was able to predict like 1 millisecond ahead of time and prevent falling down? Or for example, if a robot is able to help a person walking and then it somehow figures out that in a millisecond later, the guy is going to fall down, it can somehow prevent that fall. That would be awesome. Look at this beautiful creature, the Zebrafinch. I'm going to play some video for you here. So wouldn't it be nice if we can somehow make a short-term prediction in the singing of this creature? So for example, if the Zebrafinch says this, then it's going to say that. Well, yeah, that's going to be awesome. Hello, everyone. My name is Mohammed. I'm currently working as a data scientist at Apple, but previously I was a PhD student at University of California, Riverside, working with Professor Eamonn Keogh. Yeah, and all of my lab mates here they're not at school anymore. Yanping is at Samsung, Bilson is at Google, Bing is at Samsung, and Jesin is at Facebook right now. In this paper, we want to explore how we can explore rules in time series automatically. All right, this is the outline of my talk. I'm first going to talk about the motivation, which we had like 2 slides before. And then I'm going to define the problem statement. I'm going to talk about the algorithm, the challenges, and 5 real experiments we've done, and finally some future work. So, yep, I was talking about a robot. It would be really nice if a robot would be able to somehow predict 1 millisecond ahead of time. So we should probably do some rule discovery in time series to make this prediction happen. Here's an example. Let's say you put your cell phone in your pocket and you go on an elevator. And if you look at the accelerometer, when the elevator starts going up, you're going to see this bump, right? And whenever you reach the floor you want to get to, you're going to see this one. So this is a very nice rule in time series. We can say, okay, whenever you observe this orange subsequence here, you will expect this green subsequence coming after, right? All right, I'm going to define the problem exactly. So I'm going to use this term a lot, these 2 terms, the antecedent and the consequent. So the antecedent is this orange subsequence here. It means that if we observe this antecedent in the time series, we should expect the consequent coming after. So either right away or with a lag. But for simplicity for now, let's assume that the lag is 0. So we should expect this coming after. So the rule is going to look like this. So we're going to call this the antecedent, and this is going to be the consequent. So the consequent is the part that is going to be the prediction, right? All right, here's a beautiful data set. I'm going to call it the leaf hopper data set. I'll use this in my experiments. And some of the farms, leaf hoppers cause a lot of damage. So there's some brilliant way to classify them. What they do, they glue a wire to the head of the leafhopper, which the leafhopper doesn't bother that much. And then whenever the leafhopper sits on a leaf and inserts its stylet into the leaf, this little circuit here becomes activated. And whenever the leafhopper is doing some kind of activity, like shaking its tail or whatever, you're going to see you will see a change of voltage here from the circuit. So this is called the leafhopper data set. It's usually used to classify different types of leafhoppers. Now, here's the problem statement. Let's say we have a mess of time series data, right? And how can we discover rules, and more particularly, meaningful rules from the mess of time series data here we have automatically? So that's going to be the problem. All right. I'm going to show you a very simple example to explain the proposed algorithm we have mentioned here in our paper. Well, so a rule, the intuition behind a rule is something that repeats at least twice. So this reminds us of the concept of a motif. So a motif means any repeating subsequence. So for example, for a certain length. So for example, this subsequence here, the green one, is actually repeating 2 times here, and they're very similar. So this is called a motif. All right, let's find rules. This is how it works. So for any time series, we first run a motif discovery algorithm. It's called MK. It was developed in our lab. It stands for Moin and Keogh. I think it's the fastest motif discovery algorithm and in time series. So we're going to run that algorithm. The order of speed is n log n for this case. Now, this is a simple case. So let's say we run the algorithm and we find two sets of motifs. So one of them is the red one, and the other one is the green one. Now, what we're going to do is, in the next step, we split each of the motifs from some point. Okay? I'm saying from some point. I'll explain later how we find this. And we're going to get an antecedent and a consequent. So these two rules are potential rules. They may be not rules, right? But they may, so we're going to just go and check and see if they're good rules or not in the next step. So again, we splice it from some point, and we're going to pick the first part as the antecedent and the second part as the consequent. Okay, so we have two candidates for the rules. Let's pick the first one. So I'm going to pick the first antecedent, and I'm going to slide it through the whole time series to find the similar subsequences to that antecedent. Let's see. Okay, here's the first match. It seems that it's a very similar one. And when we go forward, here's the second match. And we go forward, no other matches. Let's do the same thing for the green antecedent. All right? Here's the first match. The second match. Well, it's kind of similar. And then the third match. And we're done. All right? So this is how it looks like. We have, so the red rule fires 2 times, and the green one fires 3 times. So which one is a better rule? And how accurate they are? That's the next problem. All right, so there's 2 main challenges here. Well, the first one is, let's say we have like 3 different motifs with 3 different shapes or even lengths. And we split them from some point. Which one is a better rule? That's a problem. How can we rank the rules? And the second problem is, there's a parameter here called max lag. So, for example, in the elevator example, depending on the number of floors that you're going up, the max lag can be different. So how should we deal with that? I'm going to go back to the first challenge. Let's rank the rules. For ranking the rules, we use, so we want to see how accurate our prediction was. How accurate was the consequent. So we have to use a kind of distance measure. Here we propose minimum description length. So we're going to use MDL in this case. Let me explain to you. So for example, if we have a hypothesis, let's say the green subsequence is here, and we have 2 other subsequences, the blue one and the red one. And we want to see which one is a closer match to the hypothesis, to the green one. What we do is we can calculate the difference between these 2 time series and then use Huffman coding to figure out the number of codes, the number of bits we need to save the difference. So the less, the better, right? And then using this term, we define something called bit saves. So the higher number of bit saves, it means that it's more similar. All right, let's go back to our example. So the red rule fired 2 times. And so we first discovered the antecedent at the beginning. And now we look after what comes after. So this is the consequent. Let's compare this to the consequent there and see how similar it is. So we use MDL to give a score to this. And this, since this one is very similar to that one, it's giving us a high number of bit saves. Now, for the second firing of the red rule, well, this is not really similar to this one, so we get less number of bit saves. Again, the same thing for the green one. So for the green one, we look at the consequent here, we compare it to our hypothesis consequent we have here, and we get a lot of bit saves because this is very similar to that. So good prediction, good job. Now the second firing of the rule, of the green rule, is like this. It's, yeah, pretty similar, so we get a less number of bit saves. And then the last one is, well, almost not similar, so we get almost 0 bit saves. Now, we add up the total number of bit saves and get a single score. So even though the red rule fired only twice, but it made more accurate predictions and got a higher number of bit saves. And the green one fired 3 times, but less accurate predictions, and it got a lower score. All right. So this is how it works. So for example, if this is if we have a time series like this, and we found the motifs, the green and the blue, we split it from some point, so we have the antecedent, the orange part, and the consequent. All right. And let's say some time series, some streams of time series comes in, and every time we look and compare the antecedent with the subsequences in the coming time series, until what? Until we get a match. So whenever we get a match, all right, we're going to say that this rule fired. So we can predict the rest of the time series. We're going to say, okay, this is probably going to happen afterwards. Let's see if our guess is right or not. Yep, pretty much. So we found the consequent. All right, I'm going to go show you some experiments we did in this paper. So in our paper, we have 5 real data sets that we tested for our algorithm. And I'm going to show you 3 or 4 of them here. So going back to the leafhopper data set, we applied a rule discovery algorithm, and we found a bunch of interesting rules. So like this one was the highest ranked rule. This was the second. And then so we come up with a list of rules. We passed the rules to an expert of leafhoppers. And then she got back to us and told us, yes, the antecedent and the consequent are related to some behavior of the leafhopper. For example, this one is when the leafhopper starts sucking sap out of the leaf. And this is when it starts shaking its tail. So nice prediction. So whenever you saw a leafhopper sucking sap out of the leaf, you can say, okay, in 2 seconds, it's going to shake its tail. And finally, the Zebrafinch example. Well, these beautiful creatures, they start learning how to sing 40 days post-hatch until 100 days post-hatch. So during the 60 days, their singing evolves. There's also a very nice paper. I mean, we got this data set from a group working on this. They have a Nature paper on this, and they try to change the singing of the birds. So we got the data set from them, and we picked the first audio file, which was like 40 days post-hatch. The first day, the birds start to learn how to sing. And we converted them to time series using MFCC. And then we picked one of the dimensions, and we ran our rule discovery algorithm on it. And we found this rule. So if you see this, you're going to see this coming right after. So for example, I'm going to play it for you. If the Zebrafinch says this, after that it's going to sing this. We don't really know what it means, but that's how they sing. And then we picked the recording, the audio file, after 100 days. So the last day which the bird is trying to learn. And surprisingly, we found the same rule as the best rule. So it's, even though the singing was evolving, but this single rule didn't change that much. I mean, the antecedent changed a little, but not really that much. The next experiment, the data set that we used is, I really like this one. It's energy disaggregation in a house. So let's say a bunch of tenants in a house are using a bunch of home appliances. They're turning them on and off in a 2-year period of time. And we have the energy consumption in this house. So it's a single time series for 2 years. We ran our algorithm, and we found this rule as the most interesting rule in the time series. And guess what? The data was labeled. So we knew that at every timestamp, which of the appliances was turned on and which was turned off. And then, so the orange subsequence here, the antecedent, was associated to the clothes washer. And the green one was associated to the clothes dryer with a gap of 20 minutes. So it makes sense. Well, the tenants in this house, they wash their clothes, and after 20 minutes, they dry their clothes. Makes sense. Well, it's an obvious rule, but I think it's a good demonstration for our algorithm. And finally, we use an activity data set, which the users were wearing a bunch of sensors on different parts of their body, and then every sensor had an accelerometer, X, Y, and Z. And we picked some of those dimensions, and we ran our algorithm on it, and we found some rules. And in order to interpret the rules, what I did was I fixed my phone here and then measured the accelerometer and looked at the time series, how it looks like. And then, for example, this rule that we discovered here was associated to drinking water with a cup, and then you're going to bring it down. So the antecedent was like bringing up your cup to your mouth and then just bringing it down. It's an obvious rule again, but demonstration for our algorithm. All right, we also compared it to other methods. So these are 3 highly cited papers. The last one was the best paper award in KDD 98, and it already has 700, 800 citations. So we, in the webpage of our paper, we compare our method to these methods, and we show that, for example, for these methods, if you pass some random data to it, it will discover rules, which doesn't make sense. But in our case, for a sanity check, we passed some random data, and our algorithm did not discover any rules. And the reason is because most of these papers, they try to explain the whole data. But what about if the data is random? It doesn't make any sense, right? All right, and well, our main contributions was here. First of all, most of the papers in this area are doing forecasting, which is trying to explain the whole data. But we do rule discovery. Maybe like you have like 2 or 3 years of data, time series data, but you explore only one rule. And finally, we try to interpret all of the rules that we explored on the 5 data sets. And we have a web page here at this address. If you want to take a look at it, we have all of the codes and data sets available here. If you want them, you can just go and grab them from here. And finally, there's some interesting ideas that we wanted to do after this, but unfortunately, I just graduated. So I will try to, work on it again. But I think the other idea is applying the rule discovery on multi-dimensional time series. And even more interesting than that, applying the rule discovery on multi-modalities. So for example, if some shape happens in the time series of humidity and some shape happens in the time series of temperature, it's going to rain. And finally, I just wanted to thank you all, and especially special thanks to my lovely advisor, Professor Eamonn, Keogh, the most knowledgeable and most supportive person I've ever met in my life. Thank you so much.
All right, we have time for 1, maybe 2 questions.
Well, no. At this point, no. Okay. This is one of the future works that we wanted to do. We made some contributions in this area, but we didn't really come up with an algorithm. I think it's more complicated than what we thought. Sure.
When you first decided where your antecedent division was and your consequence, is there any justification where you make the cut, or is there some sort of...
Yes, yeah, good point. Well, we may be able to make this more efficient, but at this time, what we're doing is we're looking at all possible split points and then measuring the MDL score and then picking the best one.
How did you justify a split point, though? How did you pick a split point?
Well, all possible split points. From like, let's say from 10% to 90% of the whole motif,
So
right?
exhaustive.
So it's like, yeah, we iterate on all values, yeah. So for example, if the length of the data of the motif is, let's say, 100 data points, we iterate on all possible 99 split points, for example.
Yeah, when you determine whether a rule has happened, when you are matching with the rules, right? Do you do any kind of dynamic time warping to find the match? Because
that's a good point.
For example, when you're drinking, when you are very thirsty, you might be drinking very fast, right? So
Exactly.
Action might be different.
You know what? And this exactly happened in the energy disaggregation problem. Because, for example, if the tenants turn on the close washer, someone will put it on some mode that's going to work for 10 minutes. Sometimes it's going to work for 20 minutes based on the modes, right? So yeah, and in this case, I wasn't able to discover all of the firings of that rule. For example, I found like only 20% of it because of the different shapes and the different lengths. That's a very good idea, because here we're using Euclidean distance to find the similar subsequence to the antecedents. But of course, I mean, we can replace this with dynamic time warping, yes. That's also some other future work. Thanks.
Okay, thank you.